So what we're going to do is the first example on lecture number 22. So this is a good example. It's not a difficult example. It's more of a plug and chug type problem. But it's a good example because it shows the difference between a conductor and an insulator. Okay, so in the last module what we did was we calculated the relaxation time, or we developed the relaxation time. So that gives us the amount of time it takes for a charge to travel outside of a contained body. So now we're going to say, well, what if that body which contains the charge is one of two things? One, a very good conductor, which is copper, and then second, a very good insulator, which is polystyrene. Okay? So what we should see is, what we'd expect is for a conductor, the charge should flow quickly, right? It should happen very fast. And for the insulator, it should happen very slow, right? Because the change in the charge is basically equivalent to current, right? So we'd expect current to flow in one and current not to flow in the other, okay? All right, so let's see if that happens. So all we have to do here is basically calculate the relaxation time, tau, which is equal to epsilon divided by sigma, right? So if you go into your textbook, it's in Appendix E, I believe, you'll find all the material properties. So for A, let's go for copper. All right, and copper, first we look and say, copper has a conductivity of 5.8 times 10 to the 7 Siemens per meter, right? So you see it has a very large conductivity, which we'd expect because it's a good conductor. And then we don't have to look up its permittivity, but we use the fact that the permittivity, which is equal to epsilon r times epsilon naught, for a conductor is just equal to 1 for the relative permittivity, right? So this is 8.854 times 10 to the negative 12, and that's farads per meter. Okay? So with these two, we should be able to calculate the relaxation time. Okay? And we do. We have both values, so we just plug it in. So for copper, we put in 8.854 times 10 to the negative 12 divided by 5.8 times 10 to the 7, and we get a relaxation time of 1.527 times 10 to the negative 19, right? So that's a astronomically small number, and that basically gives us in units using subunits 0.1527 AS, where A stands for attoseconds, right? So you normally don't see numbers that small. Okay, so you can see in the conductor, this happens almost instantaneously, right? So as soon as this goes within 5 time constants, you say this is complete, all of the charge has left the body, right? So in under 1 second, we would have all of the charge, or under 1 attosecond, right, which is an astronomically small time, you'd have all of the charge gone throughout the body, right? So in a conductor, it's happened almost instantaneously. That's a very, very small number right there. Okay? But now let's go look at the insulator. And since this is very small, we should see that the insulator should be a large number. In comparison, you'll see it's extremely large in comparison to this one. So for polystyrene, we look up the conductivity from Appendix E, and we see that the conductivity is very small, unlike the insulator. So it's 10 to the negative 17 Siemens per meter, right? So we have almost zero conductivity there, which is what you'd expect of an insulator. The permittivity is not that much different. We look it up and we see epsilon equals epsilon r epsilon naught, and epsilon r is equal to 2.56 times the permittivity of free space, right? And we get our permittivity is 2.267 times 10 to the negative 11 farads per meter. Okay? Now when we put this in and calculate the relaxation time here, we get epsilon, which is 2.267 times 10 to the negative 11, but then we divide that by 10 to the negative 7, and we get 2.26624 times 10 to the 6. Right? It's 2.26624 million seconds. Okay? 2.26624 megaseconds. Or we could say that tau is about equal to 2.6 days. Okay? So you can see the very noticeable difference between a conductor, right? So one time constant's gone in 0.1527 attoseconds, right? Which is almost instantaneously. I mean, that's as close as instantaneous as you can get, right? But over on the other side, we get that one time constant occurs in 2.6 days, right? So that's a very, very vast difference between the two. So you can see how charge flows through a conductor as opposed to through an insulator, right? And it's very noticeable, the difference between the two. Okay.